So hi everyone, it's great to be back on the GDevCon stage this morning. Before I jump into my talk, I want to shine a spotlight on Hedy Lamarr. Hedy Lamarr is, for those that are into movies, remembered as a glamorous Hollywood actress, but far fewer know that she is also an inventor. She co-created a frequency hopping system during the Second World War. And that concept later became fundamental for technologies like Bluetooth and Wi-Fi. So in other words, she influenced our everyday lives way more with her invention than with her movies. And this is what I'd like to be her known for instead of her movies. From frequency hopping, let's hop straight into our today's challenge. And I will throw that challenge directly at you. Imagine the following scenario. You have to build a software, and so you are the architect. And your requirements team has already gone and done its work, so you can read through all the requirements that are there. And you have already identified some of the modules that you need. So you need an orchestrator, so something that goes ahead and drives the sequence forwards of whatever that you need to do. You have a hardware handler that is probably there for abstraction purposes. You have something that handles the DMMs, so the measurements in your system. You need to source some power, so there's a power supply handler. And you have right in the middle, or up here, actually first a validator, so whenever there's a measurement, whenever there's a temperature, it checks whether this temperature or the measurement is in range, so it keeps all the checks and balances. And a nice little thing is here in the middle. You have the user interface, and your project is divided into alpha and beta stage. So in the alpha stage, you have to show that the process that you're automating is feasible at all. So you have to have an engineering user interface where there's tons of indicators. It doesn't have to look pretty, and so on. And in the beta phase, you have to bring that whole thing over into production. So that has to be a clean user interface that non-technical users can use and also just use for everyday production. So later on, you have to be able to rip out the user interface and replace it with a completely different one. And the question is now, which architecture do we choose? And when we go through that quote from Neil Ford and Mark Richards, that's quite liberating, isn't it? We don't have to have the best architecture. But still, there are probably 1,000 smaller and larger decisions that you have to take along the way to find the least worst combination of trade-offs. So still a rather challenging task. Keep that hypothetical system and the quote in mind. I'll come back to it. For those that don't know me, my name is Nico. Nico Naredi. I work at Silk Engineering in Switzerland, and today I'll be talking about architecting for testability and observability. Before we start building our software from scratch, or our architecture from scratch, small disclaimer and small story. I have two boys, aged 5 and 8. And sometimes we play a game when we're sitting together, and that game is called fact or opinion. For example, I would say to one of them, hey, I really don't like the drawing that you did today. And then I would follow up with the question, is that a fact or is that my opinion? And they would say to me, that is your opinion, Dad. And then I would ask another question, which is, do we care about facts or do we care about opinion of other people? And they would say to me, well, we care about facts. And I know all of us, we're not kids anymore here, but still software architecture is, in a sense, a young discipline. And it's rapidly evolving. There's new technologies, new things coming out probably every day. So what you hear me talking about today is a opinionated experience report rather than actual facts. So things that worked in the context of my project with the tools that I had available. And if at the end you'll say, well, I don't like what Nico said, that's probably fine, because my kids would say, well, it's just Dad's opinion about software architecture. So this is fine there. And when I think about opinions in software, then one of the biggest is which programming paradigms is the right one. And this is where I want to begin with the architecture that we'll be drawing. So, and paradigms for me are tools that shape how testable, how easy to evolve your system is, how observable it is. And that's not a choice that should be religious. It's a context choice. Because every paradigm that you choose creates seams in your software. A seam, just like a seam in my shirt here, is something where you can inject behavior, you can swap out behavior, you can fake things. So basically, it makes things a little easier to modify on the long run. To make that a little more tangible and stay with the kids analogy, let's compare the first programming paradigm, procedural programming, where you put just one BI after the next one, with that Duplo Lightning McQueen car here. It has two parts, upper one and lower one. You put them together and you're done pretty quick, right? But if you later want to change things, there's not so many seams in that piece of Duplo. When you take now object-oriented programming and compare that to that same Lightning McQueen, but built from Lego bricks, that, for example, makes it easier to, if you just want to replace the front window shield, you open it, you take it out, put a new one in, close it, and you're done. That's pretty much impossible when you're just taking a look at the first Duplo Lightning McQueen. So there's trade-offs everywhere, and the paradigm choice that you're making, that's not abstract, it's really concrete. And for me, the flexibility that object-oriented programming gives you in the end, that is, for me, the game changer. So I'm often reverting to that. But in the end, OOP is just a tool, even if it's a powerful tool. And it might not be the right choice in your context. Many of us learn object-oriented programming through inheritance. So I don't know how often I have seen that example with a parent class as an animal that makes a sound, and then you have a dog class that makes woof, or a cat class that makes meow. But in practice, what nobody tells you, in my opinion, is that inheritance gets messy really quickly. So we need a lighter tool, and the lighter tool is our interfaces. Everybody knows that the problem, for example, when you're building a class or just a library for one specific instrument, and then the supply chain drops for that instrument, and you have to purchase a different one. So basically you end up, although you have a class for it, you end up, because 90% of the code or of the functionality of that device is the same, but 10% is different. So although you have a nice inheritance tree, you have to rip out a few things, rewire stuff, and build from there. And that's usually fragile, and it scales terribly. Interfaces are contracts, or think of them as the electrical or the common block shape here down at the ground, because when you plug in devices, they don't care where that electricity comes from, if that electricity comes from solar, wind, or a diesel generator. They just expect 230 volts, 50 hertz, 2 holes in the wall. It's UK, so 3 holes in the wall, actually, all your devices are happy. That can be your phone charger, your toaster, your LabVIEW controlled power supply. And the same is true somehow in the LabVIEW context. What that means is basically you're coding just against a list of VIs and their connector panes. So there's no code inside whatever. So when you take a look into that interface in here, there's really no useful code in there. So basically your test sequencer, your DQMH module, they just execute the measure BI, and they don't know what is in behind. If it's a real implementation, a fake implementation, they really don't care. So we started off by defining behavior, but things usually don't stay simple. They get complex at some point. Also, you can't code purely against interfaces, so you need an object that adheres to that contract or implements that interface. And what I want to advertise here is that you leave out all the scary design patterns. The next time you have the thought of, I'll create a cluster for that, your second thought could be, I'll create a small class for it. And then you can add a little behavior to that and you build from there. And the second advice I want to give is inheritance exists, but as soon as you start building deep inheritance trees, your gut feeling should tell me, well, this is probably not the way to go. Rather build from blocks, so use composition instead of inheritance. That saved me a lot of time over the long run. So in the small, object-oriented programming keeps our code tidy. And in the large, we have to decide actually what's really important. And this is where modules and communication become the focus for me. So we started off with our interface, right? So we have our interface here on the left of our DMM interface. We implement that interface into whatever we have, whether it's an NIDMM, key-side DMM, virtual bench, whatever it is. And then for us, as I said at the last GDevCon talk, the DQMH framework is our go-to choice. So the thing about DQMH is I never really, so clonable modules and me, we never became friends somehow. I don't know why, but I do love single modules. And so what I tend to do is I take a map for those, they have already appeared in Andre's talk before, but a map is a construct of key value. So what I do is I give my DMMs a name. It could be my virtual bench or something more useful. And when I put the name in, I get actually the object that implements the interface, I get that back. So how does it work in reality in a DQMH module? Let's say I have from the outside the request to measure something. Then I just put in the names of the module that, and name of the DMMs that need to measure something, search for that name in the map, return that object, execute the measure function, and then broadcast out the result of that. If the element is not found in the map, I'm returning out the number. That is not suited for any real application, but it just shows the purpose of where I want to go. So think of the DQMH module more as a receptionist. It takes in all the requests that come along, so it picks up those requests, passes them on to the respective specialist, whether that be a simulated DMM or a real one. That real one knows what to do with that request, returns the value for a measure, and broadcasts out whatever the result of that is. And for me, that is a very nice separation of concerns, because the DQMH module is purely for communication. It does not know how to measure. That's what the object is actually for. The object knows, the DMM object knows how to measure. The DQMH module just knows how to receive and reply to that request. So we've seen how to keep our code understandable by wrapping objects and interfaces in our DQMH module. But if you remember our hypothetical system in the beginning, the communication is kind of the key. And once we have those several modules, we must make the whole system understandable. Peter Scarf, who's also here and will give a talk later on, was so kind to let me incorporate the next two slides from him into my slide deck. So he showed off these two slides when he introduced the workers framework at our offices, And what he said is, once you have several of these modules, how do they start talking to each other? And he made the point by visualizing if every module talks to all the other modules in a rogue messaging kind of way, that his opinion was that this is not the way to go. And I strongly agree with his opinion. So he said, well, he looked into the active framework, and the active framework does do it a little bit better. So he says, well, I'm just communicating up and down the tree. Still, if I look at that one guy here in the middle, just an example, I'm really not sure if I'm just passing messages up and down, if that is a useful way to spend my time. So basically, this is where we are, right, where we started off. We have modules for orchestration, for validation, our user interface that we need to swap out later on. So how do they talk to each other? If we make everything communicatable to each other, that's a mess. Otherwise, we might be a bit strict, and we can't fulfill our requirement that we can take out the user interface and replace it with a new one. So we might need a different approach. And what I did in that whole thing is, instead of wiring those modules together directly, I introduced a central messaging bus. In this case, it was RabbitMQ. So shout out to Kabul for last year's GDevCon huddle about RabbitMQ. So he gave me the idea to do that. What they do is basically all those high-level modules that you see here, they have one boundary, and this is the boundary to the message hub. That means, in a sense, they're publishing and subscribing to messages, or they're sending messages to other modules, but they don't know what they are. Is that a DQMH module? Is that a worker? Is that an actor? Is that a simple event loop that's sitting in a single VI somewhere? Or are we even staying, in that case, in the same programming language? They don't know, and probably they don't care, because all they know is the interface to the event bus. So that also means that for our user interface, here on the right side, it has a single boundary here. So replacing it, swapping it out with a different one is also pretty easy, because it has exactly that one dependency onto the message hub there. So rather straightforward. To demonstrate how a communication chain might work, let's say the step comes up in our sequence that we have to measure something. So the orchestrator fires off the command to the DMM handler to go ahead and measure. So it receives that request, passes it down to the object. The object says, oh, I did measure something. So we publish a topic towards the message hub, and the message hub looks now up who's actually interested in that message. And it sees, oh, the orchestrator needs to know that measurement is finished, so it can start executing the next step. It sees, oh, the validator also needs to know whether that measured value is within range. And of course, the user interface might need to display that value, so it publishes to all of them. And they can do with that message whatever they want. That is possible here with RabbitMQ. We just had a nice chat in the break, so that's also possible with with the message hub is basically a TCP communication when you're using RabbitMQ, but you can also stay purely within LabVIEW with the VIPM.o libraries from the messenger library and also the AMM library. They also work from that. So you can also stay within LabVIEW itself. That's no problem. What do we have so far in terms of our architecture? Let's summarize a bit. So at the very bottom of the architecture, or the top of this list, depends how you see it, we have the interface, which is just a contract and an empty shell. So there's no really logic behind that. Think of, or remember the interface of DMM just with the connector pane. And why should I start here? I should start here, in my opinion, because it just defines behavior, and it lets us later swap out implementation without too much hassle. The next layer is objects. where we implement that contract. So you have the key side DMM, NI DMM, virtual bench, a simulated one that actually implements that interface. And this is where I do my unit testing on the hardware. I get often the question, how do you split unit testing on the hardware versus, for example, in a CI pipeline? And the thing is, I do my unit testing on the hardware on that level. If I know my Karaya unit test suite works on the object and I swap it later out with an interface that is just a dummy interface, I can be pretty sure that when I later on in the real program swap in again the real hardware, it still works. So that is a very nice way to test the hardware object really on that level, on the object itself. And if you're building later on, you can swap out with a fake one. Then we wrap that object into a DQMH module, where I said we have that separation of concerns. The DQMH module is just for communication. It doesn't know anything about logic. The logic all goes into the object. So I can run a module in my CI pipeline with a fake implementation and still get a nice unit test, or in that case already an integration test, whether the communication works or not, and verify if the right messages go in and come out again. And then on the last level, these modules need to talk to each other. This is where we put the message bus in, so that these modules talk just to the message bus, where we get also the nice possibility of just faking messages. So it doesn't matter whether a message is really executed from the real user interface or injected from a unit test VI into the whole system. So far, we have been architecting really on a happy path. And this is where the trade-offs that I talked before, they stab us into the back really without any mercy. Because how do you understand what's going on in the system that is highly decoupled? And also, let's face it, we have a really all across the board, there's asynchronous processes. So let's say we have a bug in our orchestrator. Usually, or the way we learn it in the NI courses is basically that we go in, we put in a breakpoint, and then we start debugging from there. We step in, highlight execution, whatever we want to do. But quite frankly, does the rest of the system care whether we put a breakpoint into the orchestrator? Or probably not, right? They keep on running and the hardware will still keep acquiring. The user interface will keep displaying. So this is what we architected for. But now we can't, it breaks our good old debugging process in that sense. So we don't get the global picture anymore. So what we, as a trade-off that we have to do to implement now is basically we need a single source of truth, what happened in the system, and of course that's a log, right? In whatever way that is, we need from all these parallel processes, we need to make that into one sequential thing so we can replay the full scene step by step. And that means that observability is basically a design requirement from VI1. And you can take any logging library that's out there, either coming back to James Powell SQLite logging library or Jörg's, he was just here, I saw him, Jörg's HSE logger. You can take whatever you want. I decided to go with Grafana Loki. So if you ever want to open a rabbit hole that you can disappear for weeks on, go ahead and install Grafana. That is a super impressive tool. And one extension for Grafana is Grafana Loki. So this is a log aggregator that comes actually from, you know, all these Kubernetes stuff where they have tons of logs from this place and from this place and from this place. It nevertheless works nice for a locally installed application. So what you get out of the box is an extension for the Grafana dashboard. So you get really log line by log line in here what's going on. You also immediately see the log volume, so how many log messages came in, with what level, info, warning, debug, critical, whatever. And the cool thing is in Grafana Loki that each log entry comes with a set of JSON fields. And Grafana automatically sorts all those fields. So for example, each log line, as you can expect, is attached to a timestamp. And normally, if you have a log file, you can go through it and read all those timestamps. But when Grafana shows you that there's quite the break in here, right? So you can go in and investigate, hey, what is the last log message I saw, and then the first one again. That gives you a visual hint where you might want to look at modules. Or, for example, it automatically sorts them by module. So whatever sender we have or whatever thread we have, it automatically says, look, we're coming from here or here or here. So, and when you stitch all those parallel worlds, you get, in the end, one coherent story of what has been going on in your system. And so, to sum things up, we started from object and interfaces that gave us the possibility for testing on the hardware level. We switched then, or we implemented those objects into DQMH modules that made us, gave us the possibility so that these objects could communicate with the rest of the world. And the event bus, in the end, gave us the possibility to integrate whole systems with each other. And we needed for that observability because otherwise we would have lacked understanding of our whole system. So each layer that I introduced was a trade-off. Some things were easier by these trade-offs, but some things were made harder. And that's why I really like this quote, where we can really say that architecture is about finding the least worst combination of trade-offs in our project. And with that, I'd like to thank you for your attention today. Happy for any questions? Otherwise, tell me the question and I'll repeat it.
I try to speak loudly. In your messaging hub, do you have only immediate transfer of messages or some more advanced treatment at hub level?
So for RabbitMQ, there's all sorts. I mean, it's really a battle-proven thing. So basically, what you end up is you're having basically a queue for every participant that there is. And then that queue can either fill up on your RabbitMQ side or on the LabVIEW side. And then you can also message back and forth, or you can get different retry number of retries to send that message, etc., etc. So that is also already implemented there.
The routing in the message hub, that is a configuration that you have to do. So for each module, you need to define for which request is going where or which broadcast is going where. So
that's basically, it's a half a talk on its own, but it depends on what you use. In RabbitMQ, basically you have, let's call it something like a participant ID, or also topics that you subscribe to. So basically you're saying, hey, I'm interested in that, and my queue, so you're having a queue, and these messages that you're interested in, they end up in that queue. And you can either say, I, as a participant, am the only one who's interested in that queue, or other people are as well. So there we go down a little bit another rabbit hole, but you can do basically whatever you want. So whatever configuration, you can keep it super simple and say, the queue with the name Nico, only I am interested in, and that's everything, or you start aggregating things in that queue.
So it's driven by the modules that interact with that. So it's not the configuration really on the broker, but it's each of them. You can define it. From our lab, we can define it.
Yeah,
okay.
But for a mental model, so the way I explain it to my juniors in the team is, you can send basically direct messages from participant A to B. So that would be because the orchestrator knows that there is a DMM handler, it sends that there, but those hardware modules, they never know who actually is interested. So they just raise their hand and say, hey, I did measure something. Whoever is interested in that, please go ahead and do with that information whatever you want. So hardware modules in that system are ultra stupid. They don't know anything about the rest of the architecture of the system. So you can basically reuse that DMM handler, that power supply handler in any other project. Cut. Over and out, drop the mic. Thanks a lot, guys.